Okay, so now we're going to look at a quick example of multispectral coherence when we're imaging channels. This is data over the Anadarko Basin in Oklahoma, and I am Heather Beadle. I am the PI of the AASPI Consortium at the University of Oklahoma. So we'll start off trying to image these channels with spectral magnitude components. So we've blended red, green, and blue, 20, 35, and 50 hertz together. And you can see a lovely expression of these channels. And depending on if you're watching this on a phone or a computer screen, you'll probably also notice that this is not the highest modern quality data. There's a lot of noise going on, so you could probably pick up a lot of that if you're looking at this on a computer screen. So now if we move on and we look at the coherence attributes, and we're going to calculate them on 4 different spectral bands. Okay, so we're going to go from lower frequencies, like I'm showing here, where we're primarily 15 to 25 hertz, and then we're going to move up. And what I want you to pay attention to is how different spectral bands highlight different features of this channel system. Okay, so low frequency, we're moving up to higher frequencies, so from 35 to 45. Here we're at 55 to 65 primarily, and then 75 to 85. And I'm going to go through them one more time. Okay, 15 to 25, so lower frequencies. Keep your eyes on different parts of the channels. 35 to 45, 55 to 65, and then 75 to 85, which looks kind of noisy. And then 95 to 105, lots of noise in this region. So there's not much useful information to use here. And moving up again. So you can kind of step through your volume to try to identify, which parts of your broadband seismic volume are ones you want to focus on. And so in this case, we're probably looking from like 25 to 50. And so now we can look at the broadband coherence. We'll do another comparison. You can imagine that you've spent the afternoon looking through some time slices in broadband. You've picked out some incisements, which I'm showing with green arrows. We've got some noisier features being highlighted in red. And so this is just for a phantom horizon through the red fork. With multispectral coherence, where we've chosen a few of those spectral voices that worked a little bit better as interpreters, we can notice that the incisement areas, the edges of the channels, look much crisper, and the noise has been reduced. So let me go back to the broadband, multispectral. Broadband, multispectral. I often feel like an eye doctor when I do these videos. Okay, and then we can also take, if we have 3 that we like a bit more, we can do either an RGB plot, or here I'm doing a different style of blending, which is a cyan, magenta, yellow plot. So cyan colors are 10 to 30 hertz, magenta 30 to 50, yellow 50 to 70 hertz. And so you can see how we're able to pick out a little more detail. We can start using some of our spectral decomposition skills, knowing that the higher frequencies are likely thinner parts of the channel, lower frequencies thicker parts of the channel. And I'll just go back and forth from just blending it and looking at it in grayscale versus this CMY color scale. All right, so you can also do co-rendering. In this case, we've taken the CYM, and then we've also co-rendered it with coherence. So you're kind of sharpening up some of the edges, which is another great way to visualize it. So I encourage you to try this with your data, doing multispectral coherence for channel imaging. Thanks.